Hello, everybody, and thank you for joining us today. This is the third day of 3 days of extremely interesting panels. I'm glad to see we have a good crowd out here. We're going to do this in a group. First, Daniele Siragusano, who's worked with FilmLight, is going to do a first presentation. And then our guest presenter, David Stump, who's walking around the side aisle right now. He will be joining us for the second part of it. I think he's going to sit out there for right now. And I'm just going to be here to make sure that everybody's comfortable and happy. And if you need anything, raise your hands. Daniele, take it away.
Thank you, Roberto. First of all, I want to say hello from Mika. He had he should do a 45-minute presentation, and I then should do a second one, but he had personal issues, couldn't come. So I inflated my presentation to fill that the time. So we will talk a little bit longer and go a little bit maybe more in details into the subject I'm talking about. This is might sound like a strange title: Trained Algorithms in Interactive Color Grading. You could also phrase it in a more like buzzwordy term is what of those AI tools can we use in a collaborative fashion in real time? Because in color grading, where I work in, it's all about an interactive experience. So typically there are one or two colorists sitting in a room driving a computer, but then there's a whole lot of other people like directors and cinematographers in the room. And in this special configuration where you want to produce a creative flow, almost like playing in a band, like you need to get basically the vibe going to create an interesting session to improve the colors and the texture of the film. And in this setting, we looked at what of those new technologies can we use to make that session better. So I'm focusing really on the interactive use case, because there's a lot going on in offline use cases where you send something and come overnight or a few days later and you get a nice roto map or something like that. But this is not what I'm focusing on. I'm really focusing on interactive color grading. All right. So I want to first start with a definition of what machine learning is, and I think this is highly relevant because we need to get a grips on the subject in a little bit more deeper level. So a definition of machine learning, which I kind of like because it touches upon all of the important aspects, and it's from Wikipedia, so it's easy to read, I guess. So machine learning is the use and development of computer systems that can learn and adapt without following explicit instructions, by using algorithms and statistical models to analyze and draw inference from pattern in data. And there's a lot of interesting and important things. First of all, it means it's not explicit, it's not following explicit instructions in the meaning of a developer sitting down and say, algorithm do this, when the input is this, do this, when the input is that, do that. So it doesn't follow in that route. But it looks at data, and more importantly, it looks at pattern in data. So when it examines, when it's training, it's not actually just looking at a few examples, and it's not really interested in the examples per se, but in what is the overall statistical patterns in all of those data. So what does all of this data has in common? And it then basically draws inference on the pattern. And in a way, this brings us to simulation versus emulation, and I think this is also the core of what is a big difference between traditional computer vision and image processing algorithms and the new machine learning algorithms. Is this distinguishing between simulation and emulation. Simulation models the internal state to replicate external behavior. And emulation mimics only the external behavior without replicating the internal state. So this sounds a little bit abstract, but we can fill this with an example which we all in the film industry have a handle on. And this is the so-called print film emulation. On the print film emulation, this is basically the thing we do to preview what would happen if we basically take this image and we put it on a RE laser and we record it onto intermediate negative and then a print positive, and we put it on a film projector and we show it on a screen. And that print film emulation, and the word already says it, is a way to mimic that. And in order to have this problem of trying to tackle a problem, you could do simulation, you could do a print film simulation, but that print film simulation would mean that you actually program all of the interactions that lights and chemicals and photons and electrons and molecules in the film lab are actually doing. That would be a simulation because you model the internal state of a process. But what we do, because this is way too complex, what we do is we send patches, we send basically information through that system, and we look what's happening at the output. And then based on that pattern in that output, we can construct an emulation. So in a way, a lookup table, a print film emulation lookup table, is already one example of an extremely simple machine learning technique. And in fact, you could use a very, very simple multi-layer perceptron to simulate a lot, but obviously that's too trivial. But you can think of it that way. Or when we talk about image generation, if you want to render a teapot made in Utah, the Utah teapot, you could either build a model of the world explicitly by adding polygons into a simulated world, putting light sources at certain point, simulation of light sources obviously, and then a simulated camera, and then you can run a ray tracing algorithm which simulates how the lights would interact with the objects and how the light would interact, or what of those photons are captured by the camera. And that is what classical CG imagery is about. It's basically about simulating the world. Or you could use a diffusion model which looked just at a lot of data and built basically the emulation equivalent of that. So a diffusion model that goes on a prompt and says, okay, I want a Utah teapot, and it gives you directly an image, is basically an emulator. It emulates worlds, it emulates the things without representing necessarily the internal states of that. So there's no photon collision algorithm. Well, there's debate about how much of actually what the neurons all represent, but from a high-level point of view, you can think of that. So when we use machine learning, we are using emulators. And that would be actually a much better way of describing AI, because it's not using those catchy phrases that everyone freaks out of. But obviously here we are, and we use artificial intelligence, which I found a terrible name. But yeah. So in machine learning, especially in the field of image processing, there are two fields which gets heavily fueled, and there's where we do a lot of progress using these emulators. And when I say emulators, yeah, I mean artificial intelligence or machine learning. And these two fields in our industry are computer vision algorithms and computer-generated imagery. So these are the two pillars that we see a lot of innovation that's enabled us by those emulators. And my talk today will be focusing more on the computer vision side of things and not so much on the computer-generated imagery, simply because they are not at the moment so fast that you could put them fast in terms of controlling, in terms of fine details, that you could put it into an interactive color grading session. So examples of machine learning powered computer vision algorithms are object detection, object segmentation, semantic metadata, knowledge graphs, action detection, similarity depth estimation, normal estimation, and so on. They are typically fast, interactive, and provide utility. On the other side, we have the computer-generated imagery that are typically nowadays all done with all sorts of variations of diffusion models. Examples are text-to-image, like you prompt something, you get an image out. In painting algorithms, image-to-image, style transfers, text-to-video, or what we see also lately a lot is image-to-video, or the other two. These are the last 1.5 years get really out there. And if we compare the two, they are quite different in terms of a few characteristics. First of all, computer vision algorithms, they try to make the computer or the application make something understand which is very obvious to us. This is a face, this is a banana, that pixel is behind that pixel or further away. So computer vision algorithms try to infer meaning or understanding. On the other side, the computer-generated imagery algorithms, they have a more predictive or generative nature. So they try to predict the image that would go along with a prompt, or they predict the next word in a sentence. The computer vision algorithms are analytical. That means that for a small change in the input, so when you change basically, if you're driving in a vehicle on the street, and from one frame to the other frame, you want that the depth estimation also changes slightly. If you change slightly in time, you don't want that suddenly the truck is 500 meters away, and just because you changed your camera a tiny bit, the truck is now 10 meters away, and you either have an accident or you do a brake, an unnecessary brake. So we want that these algorithms behave non-chaotic. That means a small change in the input parameter space produces a small change in the output. On the other side, the computer-generated imagery are pseudo-stochastic, or you could also say chaotic. That means a small change in the input space will produce a completely different result, right? So, when you have, for example, a seed of a diffusion model, you change the seed by 1, and you get a completely different output. And they are so chaotic that there's a lot of effort trying to make those models behave again with control nets and other ways of saying, like, okay, here are some boundary conditions and please stay within that. But this is a general difference between computer vision and computer-generated imagery. Computer vision algorithms are good in interpolating. If you trained a classifier on cats and it sees a new image with a cat it has never seen, it's pretty good to say, like, oh, well, based on the examples I saw, I can interpolate, and that's probably also a cat. But you cannot ask a machine learning model that is trained on cats to identify dogs or to identify other animals. So interpolation is good, but extrapolation typically they're not so good. In computer-generated imagery, there's a lot of experimenting with not only interpolating between the patterns in the data it was trained on, but also extrapolating. Typically, computer vision algorithms, you probably interact with them when you use your phone every day. We attribute to them utility, so they're useful. On the computer-generated imagery, there's this split going on because some people are fearful, others do anthropomorphization, so they think, they give them human-like traits, say like, oh, the AI overlords will take the words and those kinds of things. And that is typically, we attribute those things agency. And agentic AI is also the next wrong buzzword I think the industry is pushing towards. Yeah. So computer vision algorithms on the one hand are well established, and the computer-generated imagery on the other side, those models, or the generative models in general, are the current AI hype. With the we believe that in interactive color grading, the computer-generated imageries the technology are not there yet for technical reasons, but also for other reasons. So because we need to understand that the models, these emulators, they mimic the pattern found in the training data. This needs to be clear, as in the definition was stated. So the diffusion models that generate images, they vary dramatically in image quality, depending on the quality of the training data. So if I take, for example, here the same prompt, a woman with curly red hair standing in the forest, no text, and I use two models which were trained on two very different data sets, we can get to very different results. If we look, for example, at the details, the high frequency details, for example, in the curly hairs, we can see some type of sharpening compression, DCT artifacts, blockiness in the actual hair here. But this is not something that the JPEG compression added afterwards. This is exactly what's coming out of the model. Because the model was trained probably, I don't know exactly, but I think so, on JPEG compressed, DCT compressed images. So that machine learning algorithm concluded that with curly hair, what we actually want is DCT compression and block artifacts because it only saw curly hairs with block artifacts. So it cannot really distinguish what are curly hairs and what are block artifacts because it looks at the pattern in the data. And because it did not give any statement about the color mood, we can also see the center, basically the mean distribution of the color mood for such an example. And we can see here clipped highlights, gamut clipped red hairs, a very, I would say, video-ish color palette. And on the other side, we see a more filmic color palette, which also gives us a clue about the pattern in the training data that was used to train these two different models. So we can see that these emulators reflect the pattern in the data. To my knowledge, no models that are available are trained on scene-referred data. That means now with the transition to digital, we have now the luxury that we have really good image quality, which relates very closely to the energy on set coming from digital cameras. But the models are not trained on digital cameras, but they are on the output of digital cameras, not at least in that amount. They are more trained on CAD videos. These are all in sRGB and are already display referred. So we will lose that relation to the actual scene energy when we use these diffusion models. And there are biases in training data, also cultural biases. I've not specified the skin tone of that woman, and in both cases I got a white skin tone because probably there's a bias in the training data towards that. And if I don't specify anything, then the mean of the pattern distribution will be chosen typically.
Daniele, can I just ask you, are these from two different sources, two different programs?
Two different programs, yeah. So
okay.
you have basically prompt to image,
yeah.
From two different models, you take the same prompt, and then you can already say a lot about the patterns in the
right.
data. Yeah,
Thank
exactly,
you.
yeah. And also there are difficult legal grounds. If you use data, you might not have the permission to train it on. Then you might be on shaky grounds. And there are tests, and the big studios are testing open source models. If they type render me a Stranger Thing of da da da, and if you get suddenly an 80s style picture, then it's obviously that with the word Stranger Thing there is the franchise associated with that, and there are lawsuits that say like you cannot use this model because obviously you have trained your model on our data. So that's why it's very difficult to do that. And also we see these models are more based on visual effects workflows. That means more iterations and chaining different tools together in long pipelines, which is typically more a visual effects workflow. That's why at the moment in interactive color grading we see less of computer generated, less of those techniques. And the good thing is for colorists in the room, those generated videos, they need rather more color grading than less. Because if you're just happy that you get the composition right, you don't worry if the colors do not match 100%. You're not going to reprompt everything to get also the color balance and the mood right. That is easy to fix in post-production. So we see from our customers' experiences that the ones that are working on with machine learning generated imagery that's coming in as source, they have more grading to do than less. Unfortunately, they are kicked back in the times of DV in the 90s because everything you get is mainly 8-bit or display referred Rec 709, so it's not as enjoyable as changing the exposure and things like that. At the moment, it's more like going back in time for a colorist, unfortunately. Yeah, so it's a new CGI technique here. And there's also a practicality that I think prevents these algorithms to at the moment to be used in interactive color grading. Because if you ask the same question to a colorist or to a visual effects artist, how much time do you have available for a shot? The colorist will tell you until the director or DP gets bored, then you need to move on. And the visual effects artist will tell you anywhere between 3 minutes and 7 months. So the time scales are very different here. But we see also with other techniques that the faster and more reliable things become, the more they diffuse towards the machine learning arena. Also, what we need to acknowledge or need to accept is that the feature film high-end motion picture is not the in the basically interest, is not in the, we are not in the interest group for machine learning. There are technologies, there's research going on, but the focus is not high-end, big movie, big screen cinema. On the one side, we have academia, and they are interested in the real research topics, making the new core architecture changes and the new components and to drive the field forwards. And we need a lot of innovation, because the last real innovation is from 2017. So from 2017, really nothing paradigm shifting has been developed in machine learning. Everything we're doing now is based on the transformer network, which was outlined in a paper from 2017. And what we're taking now, with everything we're seeing, as taking the merits from those insights. But we need more key breakthroughs to really push the field forward, otherwise we run into a saturation. And the big corporations are interested also in the fundamental questions, but also robotics and autonomous systems, when you talk about computer vision, surveillance, big data analysis. And if they go for the media and entertainment industry, it's typically for the content creator market, which is a big market and fuels basically the social media platforms and drive attention steering towards the social media platforms. And it's not really, there's not so much attention to motion picture, to real high-end motion picture. And I think this is also why we as an industry need to take that seriously and adapt the algorithms and technology to fit our purpose. In FilmLight, we have opened up our infrastructure to, so we've done a lot of fundamental work in computing, because we see that there's a lot of these algorithms, and in a way there's a lot of computation defined that needs to live outside of the actual host system. So what we defined is a very lightweight protocol which allows us and also our clients to hook in these machine learning algorithms easily into the software, and makes it easy to deploy that. Because we see it also a trend that there might be some training or fine-tuning happening on a studio level or even on a post-production level, that a post-production house as a service can fine-tune a certain model to the certain pattern in the data of the customer. So it's very important that you have a tool where you can interchange models, interchange compute platforms, and yeah, so that's just as a side note here. Okay, let's have a few examples here. So one obvious example is object detection. So what we can do here, for example, is we can use machine learning to detect faces in moving images. Why is this so important? Because 90% of the attention of the audience, and therefore also the attention of the colorist and the DP and the director, is on faces. So we spend a lot of time to get the skin tones right. And if you get the skin tones right, you can do almost whatever you want on the others, on the rest of the image. But the crucial part is really the faces. And by providing a computer vision algorithm that enables us to work on faces in a more robust and interactive way, that's highly useful. So, for example, what can we do once we have identified those faces? How can we hook this into the creative process? So now, when we want to do something on that face, we can draw a shape, for example, to isolate parts of the face. And before I do this, I attach the shape to the face. Now the shape I'm going to draw is not drawn in the coordinates of the image, but in the coordinates of the face. So up and down and left and right is not up and down in the image, but it's up and down on the face and left and right on the image. On the face, sorry. And to visualize this, what we can do, we can also visualize that new space. So now the shape's context is the face and not the image. So what we can see is an unwrap. It's an unwrap of the face laid down to you. And now what you can do is you can more precisely, for example, draw a shape on that. So again, here we try by bridging the parameter space of the colorist or the human in the loop and the machine learning technique. It's a shared parameter space, and that allows us to quickly then interact with that. So now we have a shape now which is defined in that space. Now the beauty about that is that then other tasks like feathering or blurring is also performed in that new domain. So when I do now just a normal feathering of the shape, it's feathering actually along the coordinates of the face. And that very quickly brings us to a good utility, and then you could do whatever you want in that shape. So this is one example where machine learning is empowering the creative process and not replacing it. Another thing is we can use computer vision algorithms for depth estimation to do interesting things. When we first encountered depth estimation around 5 years ago with the first open source available model, it's called meters, we looked at it, and let me do this quickly. What I do is I set up two cursors, and on the one side we will see the image, on the other side we will see the depth estimation. So this is 5 years ago, and we thought like, wow, how incredible is it? You give it a 2D monocular image. There is actually, I need to gang the cursor so they move together. There is no information about depth actually. It's all trained based on examples, and it can infer where roughly the relatively the every pixel where the depth is, or where the distance to the camera basically is. But we also saw that there's some flickering, and the edges are not perfect, and this is really pretty much of a stretch to actually use this effectively in interactive color grading. In visual effects, maybe, where you have time to finesse the maths and work with very imperfect data, that's fine. That could work, but for interactive color grading, that's probably not the right time yet. So we waited a little bit, 4 years, and then we saw the Depth Anything model. It's another open source model, and that really blew our minds. Because the temporal stability is better, we still see some cases where there are errors, there is some flickering, but we can see a big progression going on. And because we are in an exponential growth, which I'll later have a few slides about that, we didn't need to wait another 4 years for another major improvement. But in June that same year, there was another model coming up, Depth Anything V2. And this, first of all, it reduces also the video memory consumption, relatively speaking, and it increases details, temporal stability. It's also better, not perfect. I'm not saying that it's something we can use out of the box, but we can see a steady progression over here. All right? So, because we are in exponential growth, we needed to wait another 6 months for the next improvement. But then in October 2024, there was another model this time. So the other models were basically developed by ByteDance, and this one is by Apple. And when we saw it on still frames, we are blown away from the details of the video RAM consumption, everything. But unfortunately, the Depth Pro at the moment is not yet as stable as the others. So what we can see here is a lot of temporal stability issues. So while for still frames that model really excels, it's not as good in motion picture. And because we're working in motion picture, but look at the hairs, it's amazing how from just inferring of a 2D array of a three-dimensional tensor, you can basically get that map. But then, another two months later, there's Video Depth Anything. And Video Depth Anything is another model. So I need to constantly update this presentation to include the...
Like every 10 minutes.
Exactly, yeah. And this, especially for temporal stability, is a big game changer. Unfortunately, this is very video RAM hungry, so you need lots and lots of big GPUs to run this effectively. So running this as a batch process in the background is one thing, but running this interactively is really a big issue. But because of the architecture and BaseLight, we can, as you can see, I basically integrate all of those models into my system here, and I can work with them. And if a new model comes up, you don't need to update BaseLight. You update the model, and then you're off to go. Okay, what can you do with those depth maps? I mean, okay, it's nice to look at black and white images of depths and say like, wow, that's beautiful. But what can we do with that? And one example, what we could look at is changing the lighting ratios, because maybe for a cinematographer that might be something out of interest. How much do I need to actually control the foreground, background lighting ratios, and how much can I push them in post? That would be a valuable information to know. Oh, if my lighting ratios are not on spot, I can fix it in post easily for half of a stop, or for 5 stops, or for 1 stop. What is it? So we could do an experiment. Let's do this together. So what I'm doing here is I'm using a depth map to isolate the foreground from the background. And then what I will do is I will go on the foreground and I will increase the exposure by an 1/8 of a stop, and I will go to the background and I will reduce the exposure by an 1/8 of a stop. So all in total, this is a lighting ratio change of a 1/4 of a stop. Okay? So a 1/4 of a stop, as you can imagine, is not that much, right? And if we play that back, you would probably not notice a 1/4 of a stop change with this algorithm. And again, this can be done very effectively and even automated. Now let's go and let's make it half a stop. So now what I'm doing is I'm going a 1/4 stop up and a 1/4 stop down. And let's play this back. There are no obvious artifacts here. I choose my words carefully. Let's do one stop. Half a stop up and half a stop down. So this is before, this is after. And we might not see on this clip an issue here. But if we zoom in carefully here, in the motion we can see some artifacts here. Of course I've chosen that example because it's a fast, a lot of things are happening in the shot, and we are not typically as good as spotting those errors in motion. So that's why that might not be a good example to generalize to answer this question. So now if we go to 2 stops or 3 stops more, I mean 3 stops, I think it becomes obvious that this could be a Zoom call or something like that, or a Teams call where you blur the background in terms of quality, because at the end of the day the quality of that matte is not that much better than what you get in your Zoom call, and you will see that the edges really are the big problem here. So what we can do, if I go back to this, let's say 2 stops approach, we can refine the edges. There are several ways of refining the edges, and a lot of my talk will be about refining the edges. But one way of refining the edges, and I go to, let's say, this thing here, is you could throw another machine learning algorithm on top of that to do this, and I show you examples where this works. But for a lot of cases, simpler methods work very well. For example, you could blur the matte. When you blur the matte, you get rid of that hard edge, but unfortunately, you will see halos, because then suddenly some of your color correction that should go for the foreground goes on the background, and vice versa. So blurring is not really, a standard blur is not really a good thing to do. A thing we have developed is a tool for that, exactly for that purpose. For the small edge latching is a tool called Edge Filter, and the Edge Filter is like a blur, but it blurs the image. So it looks at not only the matte and blurs the matte, but it also looks at the actual gradient in the RGB image. So that tool has 2 inputs, as visualized in this little map here. So it looks at the matte, so what in comes is the black and white matte, but also the actual RGB image. And now what it does is it transfers the changes of the RGB map onto the black and white map. And this allows us to latch the edge of the matte onto the edge of the actual algorithm. So if you go basically from here,
we can see that now with that, the edges are much more aligned with the actual edge of the image. So you can also see this when we go basically from here to here. We can see we can get basically details back from the motion blur details, for example, here. And you can see that some of them might be wrong gradients, but they are gradients actually from the image. So we see more and more of the image appearing in the actual matte, right? And this helps us incredibly to push that boundary. So if we do, for example, now we ask the same question, but with that matte tool operator in place, and if we go, let's skip a little bit, one stop. And on that example here for one stop or even two stops, your friendly Netflix QC person would probably not find an artifact here, right? So, so it depends on how much effort you put on the edges here. So now even with that techniques, relighting changes of tree stop, which is huge if you do that. And obviously what we need to do now is to also adjust the flare. So the black level on the foreground are not realistic. We would need to not only change an exposure, but also change the flare, the black offset of that. But you can see of that you get a pretty good segmentation for tree stops, foreground-background lighting ratio here with an additional tweaking of the edge. So is this a general statement? Absolutely not. For this image it might work, but then there's another image here, and this is a slowly moving image with a lot of hair details here, complicated foreground and background things. And when we go to one stop or two stops, we can see the issue here that the matte is not really. It's getting some of the details, but if we really try to threshold it so that we get a decent foreground matte, we have an issue here, right? And then with three stops, it also becomes very obvious. Now with the edge filter, if we go like from here to here, and if we look, I bring this down again, and let's have a look on the edge here. And if I bring this down, you can see that we can restore some details here from the foreground, which helps to hide the effect, but we will not get this shot relit with tree stops very easily. We see lots of artifacts happening here. Even if I switch the model to a newer one, so this is the Video Depth Pro, we might be a little bit more stable, but in the end, if we try to push this very hard, then you will see that it's not going to work.
Can I ask you one question?
Yeah, sure, always.
If you don't adjust the foreground element, keep the exposure the same on that, and only reduce the background, does that change the difference on the matte? Or the edges?
Let's try that. So we go 0 here, and we go -3 on the background.
Yeah.
Let's do this. That's the reason I don't use PowerPoint. So we have, relatively speaking, the same issues,
yeah.
right? So that's the main problem.
Okay.
So how would a colorist fix this? A colorist would fix this with a combination of tools. So what we see here is, we see a wrong workspace. We see here a more nuanced relight, which is around 2 stops, but it's not all on the foreground. The colorist uses the face to add a little bit more light onto the face, and then takes parts of the depth map that actually work and exclude parts that flicker. That the usual tricks you do with if something doesn't work, you just patch it together, and we see here, and we can make a relighting of that scene, but it needs a little bit more work. And this is also important to understand that if you use these machine learning techniques, these are emulators. They will not necessarily do a perfect job on every shot. If you test it on 5 shots, it might just happen that these 5 shots resemble the patterns in the training data better than the other 2 shots you have not tested. So you need to be aware that if you utilize those technologies, that you will probably also combine this with traditional methods. And what we identified at FilmLight is that fusing the traditional algorithms and those new algorithms in a way which is interactive and ergonomic is actually the key to success. All right, let's have a look at other use cases for depth estimation. So not only foreground, background, but let's have a look at, for example, dehazing. I have this image here, and it's a really cloudy day in, don't know where this is. And if I dehaze is basically removing the haze. So if I do this is basically what I can get out of the shot. That is a joke. It was actually the other way around. So this is the actual shot, and what we can do, we can basically add haze to that. We can also remove haze, but obviously not to that extent. But giving a little bit of haze to some shots and in a more suitable manner can always sometimes sell the shot even better. So if I'm just bypassing the haze here. So that would be one use case where you just a little bit of ground fog to add a little bit maybe the second shooting day was not as wet as the first one, and just a little bit of ground fog and things can help to basically bring shots together. Another use case is combining it with other lighting tricks. For example, we have this rather backlit shot, and here the colorist used a combination of tools to taking a shape to fake a light direction. It looks really crude if you look at the shape, but if you see what it does to the image, it actually works. And then using a depth map together with an edge filter to get the edges right, to get a sensible matte, and then that allows us to then drive a classic color correction to go basically from backlit to a little bit more side lit on the face. That example here is utilizing a depth map to drive bokeh. So we have a bokeh operator which can change the depth of field, and it can be driven with a depth map, and this allows us to some extent to basically change the appearance of the bokeh. It's obviously not the same as what a lens does in projecting the light field onto a 2D sensor, but to some extent you can use this quite naturally to enhance or to make the depth of field more shallow. And so it's another example. Okay, going away from depth maps, going to another use case where computer vision can help us. That is basically grabbing and grading objects. So there are semantic segmentation tools available. Let me add one here. And this allows you to point to an object and let the machine learning algorithm spin up in the background. So what I do here is I'm basically telling or asking the machine learning algorithm, what object do you think is under that selection I'm doing here? So I can basically, and again, the focus here lies on interactivity, right? To see what the model, and also see the flaws in the model, because you want, before you do like an analysis of a whole like shot, you want to place that thing in a good spot where there is ambiguity about that. So if you place your selection here, it's a little bit unsure if the hand is the same object or not. So you can add another one to basically harden your or to remove uncertainty, or you can also add a negative pick here to say like this should not be the. So it's again trying to build a dialogue with the computer vision algorithm, and you can use this for all sorts of things. Here, for example, a typical use case I didn't really like the color of. So this is basically the untouched color of the wall, and can we change the color of some elements, because we couldn't on set we couldn't actually repaint it because it's a historic whatever building or so on, and then doing those kinds of retouches are kind of easier to do with segmentation. So we'll see a lot of that helping the creative process. But at some point you will come to the point that edges become really a problem, and we needed to include also an algorithm that is focusing really on dramatic, problematic edges. And I have a few examples here. This is a shot where probably a machine learning algorithm has nightmares from, because there's a lot of stuff going on here. And if we take a depth map here, it's fine, it's good. And if we use our edge refiner, which takes the gradients from the image and cross-talks it basically into the image, we get already pretty good detail, but there's still issues here. So it's cool how it works, but it only works for a certain range of interpolation. And you can also see that, for example, here the radius for this edge needs to be smaller to make a good result than for the hairs. And this is where then you face some limitations with the tools I showed you. But there's a solution to that, and this is it's called a trimapper. A trimapper is a machine learning algorithm which is not trained on segmentation, but is only trained on disambiguating the foreground and the background. So it's not giving you the foreground and the background, but it expects a map that shows you what is the foreground and what is the background, and then an area in between where you are uncertain. And the only thing the model does is it looks at this gray area between foreground and background and tries to find which pixel belongs to the foreground and which pixel belongs to the background. So you can think of a machine learning model has a certain capacity, right? It has so many parameters and it can only learn so much things. So if you train a machine learning algorithm to identify the foreground and the background and make good edges, then it has a lot to do, right? So it can only use the capacity it has for all of these different things. But if you have a machine learning model, which is the only job it has is to look at the edges, it has more capacity to do so. So it will be better than the generalist model that tries to do everything basically, because it can focus its whole attention or its whole computational expressiveness, if you want to say, to tackle that one particular problem. Expert systems, basically. So what we do is we provide a shape, a black and white shape. It's also it's a neat thing to interact with this model with tools that you have in BaseLight, because you can draw a shape, right? So in this case, I draw a shape, so this is the best as my roto skills can get. So it took me like 20 minutes. No, I'm kidding. This is a very rough mat. And then I feed this mat and the original image into this mat refiner algorithm. This is a machine learning algorithm. And now what it does, it goes basically from here and it produces basically this output. So the only thing it really does is it looks at the gray area here and then produce this. And now if I use this for my selection, it's computational expensive, obviously. It's so interactive in BaseLight because BaseLight is an extremely powerful caching system. So you can basically do these analyze passes before the grading session happens, and you can rest assured that your caches stay active, and you can rely on them and click on them, and they will be there. And then have the interactive, rather simple color grading then on top of that. So now I can, because I have that, I can now change the exposure and the white balance and can do basically whatever I want on the foreground and background. This gives us extremely creative freedom. However, you will see that if you have that level of flexibility, you will see that the image itself will impose some limitations to how far you can push it, obviously, because if I make this too dark or too bright, even if the edges are perfect, it makes no sense photographically.
Is there a specific ratio of light that you have to stick with to be able to go this far? Meaning a 2 to 3 or 1 to 4, key to fill?
I haven't found a rule of thumb yet, because it's really depending on, if you have extreme strong lighting, then you will see changes in lighting much quicker than if you have like diffuse lighting,
yes.
Right?
Okay.
And so, but this is a good research area.
And color, color also, does color affect it?
Yeah. Color at some point, that color would be motivated by some spill light or something like that. And if it isn't there, right, then you. So, but that's pretty powerful. And the good thing is you can produce this matte, not we are rotoscoping, but we are other machine learning algorithms. So what we have here is, let me bypass this, for example. I'm using the segmentation in, let's drill down here. So I use basically, let me go here. I used a segmentation tool that one I showed you with, like with the isolating different objects. And this is the mat I'm getting here. And you see the mat is not really good. It has some, in some frames it has some artifacts. You can see the convolutional neural network layers appearing here. So they're working in blocks and in convolutions. You see them appear, which I find very interesting. But anyway, but this is not the final mat I'm using. It's actually not the mat I'm using at all. I'm using this mat just to guide another machine learning process. So what I'm doing is I'm feeding this with a little bit of blur and a little bit wider radius for the foreground. And I'm feeding this into that second algorithm, which then disambiguating the foreground and background for me. And then I'm getting basically this mat here. And depending on what you do with that, and she loses here her legs for a second, but I left this in on purpose because you will not notice in that image here because it's so dark that you might not notice that, depending on the color grading you're applying on that. But you can see that we can now do this relatively stupid color grade. It doesn't look real, obviously, but just to make sure, just to show you how even fine detailed hairs can you can produce a mat. So now, is this an interactive color grading element? And I think this amount of work is kind of the edge where what a colorist would do or a color assistant would do in a grading room. So let's say you have like 4 shots where they are not moving and 3 shots where she's moving, and then for these 3 shots you go to this kind of techniques we believe this kind of works, especially for commercials, but also for long form.
And this happens always in real time, like you're showing it.
Yes, exactly. Yeah. So I mean, these algorithms, they are not real time. They are, depending on your machine, half real time or quarter real time. But then you can cache them up, and then for the creative work,
Right.
But we're not looking at algorithms that take seconds for a frame. Everything that stops the creative flow really is not. Can be used, but not in interactive color grading. Another example here where I use a simpler stack. I use basically the segmentation tool and feed this directly without any further tweaking from myself, and just to get the hair details here. And then I'm using a bokeh to drive the bokeh of the shot. So this is basically the bokeh gets more at the end of the shot. So it's basically the kind of the she has a stressful moment or realized something, and now we're focusing on her. You can scale this from semi-automated all the way to half manual. So when we have this shot here where the ambiguous elements of the shot of foreground and background is half of the shot, half of the area here. So all of the hairs here needs to be basically disambiguate. And how I did this shot here, this is I used rotoscoping and tracking to produce this mat. So this sounds a little bit strange. How did I come up with adding small blobs and moving them by hand or tracking them over here? But when I created those blobs, I actually looked through a process that fed that mat into the mat refiner. So while I was changing the individual elements here, I looked at directly the result of the machine learning algorithm. So I saw, okay, there's a strain missing, and okay, then I need to assist it only here a tiny bit. A little bit of information is enough to basically help the algorithm to disambiguate the foreground and the background, and then using subtracting a gradient here. And this allows us to then do basically a color grade where in this case the background is foreground background lighting ratios are changed by 2 stops. So we see there's a lot going on, but at the end of the day, we need to acknowledge that these algorithms are not working 100% out of the box, and we need to combine them. And for different shots, we might need a different recipe. And we humans are actually quite good in learning that, I must say. And our users are embracing those tools and are doing incredible work with that. Okay, a few other things to look at. One is optical flow enhancement. So this is another computer vision algorithm. Optical flow is trying to find where is the pixel the same pixel in the next frame. And with optical flow, you can drive, for example, retiming. So I have this shot here where I use a optical flow retimer, which using machine learning model, and the amount of foreground and background disambiguating and the work with on fine details. You really need to look. I mean, you see a little bit of errors here and there, but this is also an extreme slowdown of 0.05, so from 100% to 5%, and that's unseen of to do such retimes with optical flow. And with optical flow, we can do all sorts of other interesting things. We have a thing here, for example, where we can interpolate frames. So even whole frames, basically. So what would be a use case here? Maybe she's blinking 3 times here. So 1, 2, and 3. So what if we want to remove that blinking? We could, for example, interpolate the frames where she's blinking. So we have this flow blend algorithm. And now what I'm doing is I'm not only interpolating the eyes, but the whole frame. So the frames you're seeing here are, when the cursor is in the green area, these frames are completely interpolated from the surrounding frames. So, and if we play that back in real time, we can see that this can be. And I didn't actually bother to put a shape only to on the foreground, but all the chairs and all the lights and everything is basically interpolated over 7, 8, 9, 10 frames. A more realistic use case is that type of scenario where you have this moment, should he grab the bag or not? But then the attention is stolen by that really unimportant car in the background. And how do you remove that car? Typically, you would take a still frame, you would comp that in, and you match move it on top. But then if the focus changes slightly, you will need to then adapt that, and you think it takes 5 minutes, but then it takes 20 minutes or half an hour to actually get this. And what I've done here is I've basically did the same thing, and I've interpolated a huge range here of frames. And I restricted the interpolation only on that area which is actually needed. And now that thing is gone. So these little helpers can, by improving the computer vision algorithms, we can do a lot of interesting stuff there. Okay, some other use cases. Where might we go from there? And this is a little bit of an outlook into the future. This is not something that is in FilmLight at the moment. So everything I showed you here is in FilmLight version 7, which is in public beta at the moment. So always we tell our customers don't use beta software in production, but we know our customers, so we could say this is already in production. What we're showing you now is not in production yet. We looked at machine learning techniques to, for example, how can it help in the realm of look development. We have a tool called Chromogen, which is designed for look development. So it's a tool that allows you to build looks from scratch or to mimic filmic looks or other looks. And a few years ago, when we introduced that, we said that we believe that with Chromogen, because of its natural system design, is able to mimic all of the film looks that are out there, or almost all, but much more as well. And we wanted to prove that. So what we've done is we made a machine learning algorithm where you give it any look. In this case, I'm using a basically a print film emulation, and that look that doesn't need to be a scene look. That means it doesn't need to be an HDR look. It can also go from log to Rec 709 or whatsoever. And you give that machine learning algorithm that process, and what it will do is it will, let me put a second cursor in here. It will come up with a chromogen configuration. So this is now the same look, but now fully open and tunable and HDR and scene referred. So it will basically, if I flip between A and B, you will see it. If you carefully look, there are some minor, tiny differences. But overall, if you do a butterfly, you can probably not say which one is which. And especially in the skin tones, we put a lot of training onto the skin tone. But now the good thing is that thing is fully tunable. So you can now go in there and see actually that opaque LUT you used for the last 20 years. What does it actually do? And then you can go in there and say like, oh, the greens are getting darker. Maybe I want to do this more or less. And you can modify your look. And it's a different thing if you go actually in the middle of that look process and change how the greens get affected than adding a color grade before or after to look to make the greens brighter or darker, because your change affects basically all of the stages that this look is composed of. So this is a much more pure way of then modifying your look. So especially for the look development process, this is highly interesting. So here that's basically the Earthy film, and here we have a Kodak Vision emulation. And we're not saying that we want, let's say like everyone should use that Kodak Vision emulation, but it's a starting point from where you can explore the parameter space, right? So why are people using still a film emulation for creating looks? I believe it's because it gives you a good starting point, and from there you can explore the parameter space. And in digital, you can explore the parameter space much better than in analog times. In analog times, you could run your negative through a process and then maybe do it another time, but only in a test, really. And if you did something on the chemical side of things, you better tested it before. But in digital, we can explore the parameter space without any consequences. We can test all around, and I think this, and this is featuring and that thing. So you can take a familiar starting point and then from there go on. We could also mimic a more modern look. So this is the ARRI, the look that is implied in the ARRI display rendering transform, and we can also mimic that here with the same algorithm. So we didn't come across, and we tested it with over 800 looks we have in our own repository. We really couldn't find a look where we couldn't find a good chromogen fit for that look. So really, we believe that the parameter space of chromogen is really Turing complete. That means you can produce almost all of the preferred looks with that. And I think that opens up quite a few possibilities for colorists. All right, so this is also where we can use machine learning to empower creativity. Another thing is also we can cut off boring tasks. And one boring task is so-called conforming, when you take the movie from one system to another system, and all of the decisions that are made there, other than the edit decision, might get lost because of our industry not really talking to each other. But we have an issue, and I'll open another scene here. In high-end post-production, we have often the issue that you get a play out from editorial, and then you conform the media, and you realize, oh, there are some resizes done to the actual images in editorial, and these are not reflected in the edit decision list or AAF or XML, or if they are, different tools use different ways of expressing transforms. The one used the origin in the middle of the image, the other one used the origin in the corner of the image, and the one using spline algorithms to do keyframe animation. And so it's a mess. So and there's a lot of boring tasks that do this kind of conforming, making the online conform to the offline. And we throwed a little bit of computer vision algorithmic onto that problem. Other could say, why didn't you wait for Open Timeline I/O? The reason is we don't believe that Open Timeline I/O will solve that issue. That's why we've thrown a little bit of machine learning algorithmic, computer vision algorithmic on top of that. So what is So this is basically an example where every shot needs a transform matching. And so what we do is we add a transform to all of those shots. And in there we have a new section, transform matching, and we say like, okay, look at the offline. So we have a role in our track system where you put the offline, and now match basically the scaling and the frames for all of the shots in your timeline to the offline. And now we're in a flip between the offline and the online, and we put watermarks, time code. We also did heavy DCT compression on that. So if you use Swift feature detection, then it might work for uncompressed media or very similar media. But if you add block artifacts to and the softness of that comes from like playing out stuff which is already compressed and generation loss, and we basically can now match very easily the frames here. This doesn't work because here there's a keyframe animation. So, it's not a static transformation. But we also looked at this. So we, instead of matching the frame, which you could do basically for many shots in your timeline, but if you come to a shot which doesn't, where it's a dynamic, you can also say match strip. Now it will basically try to find the least amount of keyframes to actually make the whole sequence match. So because this one was literally just a drive-in, a zoom in, it find the right presets and the right interpolation mode to do so. But it will add keyframes to that. So even if you do a more complex thing, it will go all the way until, even if it's like a stabilization or something, until you have a keyframe for every shot. So here it found the right transform for all of the shots, and the only thing you need to do is you need to basically comp them on top of each other, and then you get this split screen. I mean, this is a thing that a poor conforming online editor by hand will take 5 minutes just for this one shot. Like with looking at mostly gray images, because the diff between is gray, and then if you see gray, you accomplished your task. How sad is that? Anyway, and here it adds a mark and says like, oh, it couldn't find a good match because this is not a 2D transform, but it is a perspective transform. So we added also the same matching algorithm to our perspective operator. So we say match frames. And now it will do basically an affine match. Now the only thing we need to do is comp them on top of each other. And this algorithm is pretty robust also against dramatic zoom-ins. So it's almost scale invariant, which makes sense if you look at the architecture, but I don't want to go into the details here. Extreme zooms in here. Zooms in, and here we have basically a strong color difference. So here we have a black and white and a strong zoom in. So it's really robust against color changes, because typically the editorial, you get already color graded rushes, and sometimes the contrast from the offline is so much different to the actual ungraded material that you want that thing is robust. Also extreme zoom outs for picture-in-picture work relatively good. So this is another example. Let's close this again, where we use computer vision to not only strictly interactive color grading, but the preparation to that as well. All right. So I think the last thing I'm showing is, this is, I think, a premiere where I think we haven't showed this in public, but we also looked at the use case of shot matching. Let me open up a scene here for you. So this is an example here. So let me get rid of that. So what is the task? The task is we have a sequence, and the sequence might not match. The shots might not match to each other because of various reasons. And what we are looking at is, let me kick this off while I'm talking. Don't need a report here. Whatever. Don't worry, this is still in development. That's why we have so many parameters here. It will be. So what we're doing is we're using computer vision algorithms to build a scene graph. That means we try to understand the overarching relation of objects within a temporally and spatially consistent scene. So we try to identify with computer vision algorithms, okay, that person is that person in this shot, this person is this person in this shot, and try then to build classes of, okay, that's all the same person. And then we can look at for example, with the face detection, we can look at the color of the faces and can say like, okay, if the same person is at two different shots, too close to each other, then they might also have a similar skin tone. We look also at the overall mood of the image. If a whole scene is dark and blue, we acknowledge that fact that it might be intended that. So we analyze the average mood of a scene, and this gives us an idea of what the intention was, right? So we can move everything. When we change the balance of the shots, we're not trying to make them all neutral or something like that. We want to keep the aesthetics that is in the material. But for this, we need to analyze the mood and come up with, okay, what is the actual mood the DP has intended, and this is our guidance for that. And then we do things like segmenting also elements. So, for example, that lamp here appears and also here in this establisher shot, and by grouping and clustering algorithms. So let me go to the scene. So now what it's done is, as a result, it's not just match the shots magically. No, it inserted a color grading operator. The primary color grading operator you should use for balancing shots. And this is a base grade. It's highly important that the output of a machine learning algorithm is not an opaque thing that you can take or leave, but it's just a suggestion to a parameter space that a colorist can fine-tune. Because you will see, also in this example, a colorist with critical eyes will not agree on all of the shots, right? It will not say that all of those shots will match to each other 100%, but it should give you a better starting point where if one shot falls out of, or 10% of the shots fall out of the range, you can quickly interact and say if that one shot maybe it's a little bit too red or a little bit too magenta. Instead of doing that from scratch, you can just assist it a little bit. So we want to cut down the time it needs, not the actual process, but the time it needs to complete the task. And so that one shot would be probably a little bit too dark, and I just can make this a tiny nudge brighter and then move on and maybe a little bit warmer. So this is another thing we are looking at to use computer vision to make the
to put the tasks back in the hands of the colorist to actually spend the time where it's important,
exactly,
and let the machines do the rest, the grunt work.
Yeah. So the last example, this is more also an experimental thing, just to show you where technology we believe is not yet there, even if others are claiming it is relighting. Let's try to come back to this very hard shot here. Let's try another thing, and probably because it's so experimental, baselight might explode, and then I will just very calmly go to the question section, but maybe it works. What I will do is I will add a relighting tool in Baselight, and I need to give it kind of a scale. And now what we can do is we can basically place the light into the room, so it basically reconstructed as a 3D environment of the monocular image, and you can do you can place the light, and we thought a nice interactive way would be that on the surface, perpendicular, you basically go out to put the light source here. So that looks awesome for a demo. If I not zoom in and I don't press on play, but let's do that. So I'm adding an artificial light source basically to her left. But you will notice two things when you really carefully look in here. Loop mode shot. first of all, what is nice is that when she turns her head, she gets hit from that light, but there is a lot of flickering happening in there. And that flickering is modality flickering. That's even worse than normal flickering, because it's not that we have a normal flickering. No, but to do this, we need different informations from the machine learning, from the computer vision algorithm. We need normal maps, we need world position maps, we need depth maps, we need kind of different layers of information. And these layers, they are not temporally coherent to each other. So we call every every path is a domain, right? And then we have basically interdomain flickering here, or you can call this also a modality. Normal position of surfaces is a modality, depth is a modality, and then we have this intermodality flickering. And there is no algorithm, no machine learning algorithms that give you a good temporal agreeing upon modalities that you would need for relighting. I mean, you can relight on your phone a picture you sent on Instagram or something like that, but we see this technology, while we have the infrastructure and the framework to do that, this is not something we're shipping in Baselight, because it's the supporting technology is not there yet.
There are some specialized programs that are offering that.
Yeah.
Now, I'm supposed to be using that on a project. I haven't done it yet, so I'm wanting to see how effective it really is.
Yeah. You will probably get very accustomed to intermodality flickering, because this is what they all have.
Okay.
You have a static frame, a static shot. It works good, but then and in here I'm not having a big of a movement, but it's it really depends on the shot. Right. So, but if you say like, so machine learning is not actually, we cannot use that. There's one thing we need to remember, and this is now bringing us to the end of the presentation, where, I'm almost filling the 1.5 hours. So we are in an exponential growth at the moment in the research and in the innovation of machine learning, and no matter what metrics you look at, you will see the same exponential graph. One example, if you look at the papers published, the scientific papers published on arXiv about machine learning, or that use machine learning techniques, and you plot them over the years, you will get on a log-to-log plot. So basically, the y-axis, you could scale it linearly, so 1,000, 2,000, 3,000, 4,000, or you can scale it logarithmically, so or in our words, in densities, so 10, 100, 1,000, 10,000. And if the y-axis is logarithmic, then a logarithmic growth is a line, and so we see a perfect line here, and if it's scaled linearly, then you have this exponential curve here. So that means from 2007 to we had basically, let's go here, maybe 10 or 10 papers, and then 6 years later we had 100 papers per month. But then another 6 years later, we do not have 200, but we have 1,000. So in the same increment of time, we get always an exponential growth here. Numbers of GitHub projects, same thing. So if we hit the 500,000 projects here in 2019, if you go 2 years later, roughly, a little bit more, you are at 1 million GitHub projects published, machine learning projects published on GitHub. So 500,000 projects in 2 years. Now, if you go another 2 years, you're not at 1.5 million, but you are at 2 million. So every 2 years, we double the amount of GitHub projects. Crazy, isn't it? Or you could look at the computation that is required to train those foundation models. We can see a straight line here. So we need to look at the y-axis, and tada, we see it's basically scaled logarithmically. So this is basically the petaflops, 1 million, 10 million, 100 million, 1 billion, 10 billion, 100 billion petaflops to train Gemini Ultra. What does this mean? That's why the other slide is even more important. Petaflops is basically, you can translate this to money, because it's energy you spend, computation resources. And if we look at the same graph of foundations model, but how much the training actually costs, then we can see that you could, with 1,000 euros, only a few years ago, you could do something interesting, right? But then 2 years later, we are at 100,000 euros. Another 2 years later, we are at 1 million or even 10 million, and now we are at 100 million. So the money spent on training on the same amount of time is tenfold. It's crazy. Yeah, number of foundation models, same thing. Number of patents, it's also interesting. The amount of patents that are filed is also doubling every year almost. So there will be probably AI lawyers fighting AI patents. I don't know how this goes. Interesting is also if you compare the patents in different regions. So this is China, this is European Union, and this is United States. We see that we are all at an exponential growth, but others are maybe a little bit ahead in certain areas than others. All right, so I think I skipped that 2 slides and come to the conclusion, to my last slide, and then we open up for questions. So computer vision, we believe, improves how we can interact with a computer. Both creative and productively enhance the experience that we interface with computers. Computers become more natural to use with those algorithms. These algorithms, we need to be aware that do not provide 100% success rate, and we might be prepared to use different techniques for different shots. And there is not this, AI will solve everything and you only need this a one-click shop. This is not what we experiencing. Yes, still challenges with temporal stability and edge handling, but they are also good. We have good handles on that, and we are in an exponential growth. Yeah, we believe that the output of algorithms should be understandable and tunable. On the other side, computer-generated imageries, there are various technical challenges that are addressed. We are also in exponential progress there. If you look at Veo and all of the other content creation platforms, there's incredible amount of innovation there. But there are also non-technical and legal challenges. And at the moment, we see these computer-generated imageries more in the visual effects world. So if you are in visual effects, I would definitely get my hands on that. But the good thing for us is those computer-generated imageries, they need more grading rather than less. That's why I have a positive ending for my slide here. And open up the floor for questions.